a project proposal. So thank you. Some of you have it, and I don't understand that. But there were no points, so I guess that's okay. But there are points coming up really soon on writing up the summaries of the papers. So like you have to get your project proposal approved to be able to do that one. So there's just a handful of you that didn't do it, like 3 maybe. I don't know exactly yet, but yeah. Was there a question?
I was just gonna say, is it just one? Do we all for you, or just
no? Just one for your group. Okay. Yeah. And some of you formed groups using Canvas. Thank you. Most of you didn't. So I formed them, and that was kind of annoying. But at least Canvas has all these tools. Like the interface for doing that on Canvas was really pretty great, but whatever. At least it's there. I have looked at probably all of the proposals, and for the most part, they look really good. Some are like, they look really hard, so like, good for you. But I'll probably say like, don't do that, or like, do less of that, or something. So yeah, and if you want to do the full thing, wow, go for it. That'd be awesome. Remember that you want like the best I can do in terms of hardware for you here is, collaboratory or $50 per member of your group on Google Cloud. So however you can make that work, that's great. So only one person's emailed me for instructions on Google Cloud, how to get the Google Cloud credits. So if you feel like you want those, just email me and I will send you information on that, okay? All right. So let's get started. Any questions before we get started? Is there a question? No. All right. So so we had kind of a little bit of a change from plans in the syllabus this last couple of weeks, and what I just decided to do is just pick up right now where it says we are in the syllabus. Which is this week on Tentative Models, and you already had a preview on this stuff from Alessandro, I guess a couple weeks ago now, and that's great. I'm going to go into a little more depth and do a few more things on these different kinds of models. So hopefully the preview will be helpful to understanding what's going on today. These models, I think, are some of the most interesting models right now. Just in modeling, but like in particular in neural networks and how neural networks are being used to model very complicated probability distributions and that are used to generate images. And at the same time learning like very interesting latent structure for the data set that you are modeling. And it's also really cool because it's essentially an unsupervised technique, although done in a supervised way. Like all these are like unsupervised techniques done via supervision, which is also kind of clever and just pretty fun. So let's see here. I always get this wrong. Yep, so that's the one I shouldn't turn on. There. Okay. So we're going to do 2 parts of this, generative models. So here we go. So we talked about this at the beginning of the class, at the beginning of the course, just supervised versus unsupervised learning. Basically, up to this point, everything we've done has been supervised learning. It's mostly been classification. We really haven't done anything besides that. And the reason for that is because it's like, well, there's lots of really interesting problems, obviously, that are supervised. But also, like, these are probably like the easiest things to train. We have a really strong supervised signal for your loss functions, and you get really good, strong gradients that allow you to learn really great estimators. So, and there's lots of great labeled data these days, and some of it is publicly available, and some of you are using it for your projects, so that's great. So we've gone through lots of different things like this. So, classify the thing in the image. Find all the things in the image and then classify them. semantic segmentation. So for each pixel, saying what class it belongs to. Caption an image. These are all examples that we've seen and you're doing in homework on supervised learning. So in each case, you have some data. So like in this case, our image, and there's some label associated with that. In this case, the caption, and we have put together neural network architecture to allow us to learn that relationship between the input data and the output data. So, the output table. So, in many ways, like supervised learning is really just what you might call function approximation. There's just, you assume there's some function some very complicated function in most cases that takes you from input X to output Y, and your job is to learn that. And neural networks are particularly good for that because, one, there are some theoretical guarantees that neural networks are universal function approximators. So if a function really existed for this, then you should be able to find a neural network architecture that can approximate it as well as you want. It might be too large to train on hardware these days, but at least there are theoretical guarantees that exist. And a couple of that I just said it, but there's great hardware that allows us to think about not just a few layers of a fully connected network, but we're now dealing with much more sophisticated networks like convolutional networks and recurrent networks like LSTMs. Okay, so that's all been supervised. So now unsupervised learning. You just drop the Y. We don't have the labels anymore. Now all we have is data. So some of you might be like, I like this because there's no Y's. It's just data. It just seems simpler. But it's actually it's way harder because instead of there being some function you're trying to approximate, now what you're hoping to do is try to learn some underlying structure that describes the data. And there are various ways of thinking about what it means to learn this underlying structure. So a simple example might be simple clustering algorithms like k-means. You sort of come to this, you think okay, well there might be k clusters. There's an algorithm so if there really are k clusters and they're sort of separated in nice ways, here's an algorithm for learning that. But it doesn't work too great for a couple of reasons. One is it's hard to choose the right number of actual clusters. It's hard to know that a priori. And then, this works great for a couple of features, but if we have a really high-dimensional space, this actually doesn't work well at all. And in general, unsupervised learning doesn't work well in high-dimensional cases because you're looking for notions of similarity, but in high dimensions, the typical notions of similarity really break down. You have cursive dimensionality, you've probably heard of before, kinds of problems, and it's actually really quite difficult. There are dimension reduction techniques like PCA, principal component analysis, that you're probably familiar with, where you learn the axes of most variance in your data, and it's a change of basis from your standard basis to this new basis. And in this new basis, you hope that you can explain most of the variation in your data with far fewer principal components than the number of dimensions of your space. So therefore, reducing the dimension of your space and hopefully making clustering easier. So now you start doing clustering in these lower dimensional spaces. Sometimes this works great, but most of the time it doesn't, especially when you're using data that's way more complicated. So images, this doesn't work, right? There's not a good way to PCA images unless the images are you do a lot of pre-processing to say they're all very similar to each other, faces, and you take the time to crop them all to be the same size, roughly the same view of the head, and then maybe you have some you can expect to do some sort of PCA type thing, but that's not guaranteed. Something related to PCA, but that is that can be implemented in a number of ways, including with neural networks, or at least with nonlinear transformations, and we'll talk a lot about today, is this idea of autoencoding, where the idea is to learn to compress whatever your input data is down to some latent representation, so usually of a smaller dimension, much smaller dimension. And then from there, so you think of this as like going from a high dimensional to a low dimensional representation of X. And then you want to decode that. So you go back to the original dimensions, but only using the information that you have in this lower dimensional latent representation. And then the supervised signal here is just the reconstruction error. So you just take your original image and you pass it through this, what's often called a bottleneck, like neural networks, a bottleneck layer, so an information bottleneck, where you're compressing all your information that's in, like, say, your image down into some low dimensional representation and then come back out again. And then you just look at the difference between your input and what you decode from the latent features, and you just penalize that like in an L2 fashion. So you're just saying, like, make these as close together as possible. And what's cool about that is you're doing dimension reduction, and it feels like it's unsupervised because there's really no labels here at all saying, like what each pixel is or what's in the object. You're just using the input data itself as like labels, as like as the thing that you're trying to predict, and you're using that in a loss. So you can actually train these like in a supervised way, or like using stochastic gradient descent, as we've seen many times. But the task here really is just to take this high dimensional representation and embed it in some low dimensional space, hopefully preserving all of the variation necessary so that you can decode back to the original. It's a really powerful technique that we're going to talk a bunch about today. I guess you've already talked a bit about, but also I'm going to talk a couple of days, a couple of lectures ago. And there are other techniques sort of related for doing density estimation or sampling from distributions themselves. And these include things like generative adversarial networks or GANs that you also heard a bit about. And then we're going to talk about, not today, but on Thursday. So anyways, we have these two different types of machine learning. And when we talk about generative models, we're typically talking about unsupervised learning, even if the way the generative model is created, is trained, is through like a typical unsupervised framework. What's nice about this, of course, is that when you have no labels, you have no need for like, Amazon Mechanical Turk or something like that to get humans to sit there and label and say, there's a dog or a cat or whatever in these, or an expensive physician to say, there's a lesion here in this tissue or there's not. And of course, like if you could do this for real, like this would be awesome. Like if you could really learn like some perfect low dimensional representation that allows you to capture all the important variation, say like in images, then you wouldn't need all the labels. It would basically like discover the labels, or these things might naturally cluster, like images might naturally cluster together in like birds and cats and whatever type of ways, because it's just like it's a factor in the images that is being learned during unsupervised learning. Okay, so let's talk more about generative models. So why we call them generative models is that we are typically trying to learn a model that will generate data. So we have data. We want a model that will generate it. And that might kind of seem funny, but if you can generate data, that means that, and that data is like, when we have a data set, we often frame this problem as like these images are drawn from some sample, some like larger sample of like the things we care about, right? So if we have 1 million ImageNet images, these the data there is, think of each one of those as like some sample from a distribution of like images that, from data that represents images in the real world, things that you might take a picture of. And if we can learn a model that will generate other things that look like images in the real world, we can say that like we've learned the important relationships in that data to allow us to do that. And then we can say we've got this model that will generate our data. And like a typical framework for thinking about this is something like I was saying, the training data, we typically think of this as like being generated from some distribution. And what I mean by that is like, just like if you take an image, like say 256 by 256, you can think of like all of the vectors 256 by 256, or matrices, I guess, or tensors in three colors RGB. You can think of all of those, all the ones possible. So like every value you could put in any one of those entries, like that would be some data of this form. But not all of those are actual images of real scenes, right? So the probability distribution on top of this is saying like on those pixel values where it looks like a real scene, like the probability is high. Like if it's, the probability is saying like, probability that this is actually like a real picture, like a photo of a real scene. That distribution is giving you that probability for each one of the arrangements of those pixels. So like if you imagine it for like most of this really high dimensional space, the probability is going to be 0. Like they just don't represent anything in the real world. But then like it gets to be around like some arrangement of pixels and there's a dog in there, right? So the probability distribution is peaked and it's higher on that arrangement of pixels. And everything nearby it is also going to be high because like you can make some, if you just make some small tweaks to the pixels, it'll still look like a dog. I mean, eventually if you make enough tweaks, it doesn't look like a dog anymore, right? But that's the idea. Like that's the idea of this probability distribution. And if we can learn to like so if we can learn to approximate it, or at least learn something that allows us to sample from it, we can say that we're learning something about what it means to be a natural, or to be a natural image within this like huge high-dimensional space of pixel values. Does that make sense? Is the idea? Yeah.
So the pixels, right? Do we assume that they're each independent from each other in this probability distribution, or?
Well, you don't have to. Like this is just, think of this as just the joint distribution of all the pixel values, right? So this X is like a vector or matrix or tensor of all the pixel values for each image, right? So it's a joint distribution, and yeah, you're right. Like it can't just be like each image or each pixel is independent of the other one. Like that isn't like you couldn't factor it that way. That wouldn't be correct. You might do that to like try to approximate learn something, but yeah, this is just saying this is like a joint distribution over all the pixels. So there's the data. So you have like, so this is like the actual distribution from which we have some sample of data, and this is the model that we're trying to learn. So this is going to be like our neural network that's learning to tell us, either we have an explicit model. So it's going to, for each arrangement of pixels, it's going to tell us, whether or not this is probable or likely. Or it could be, we don't really have an explicit form of this, but we can sample from it. So we can just like generate things from it. So what we're doing is we're generating arrangements of pixels that have high probability under that distribution. So like those are the two different kinds of things that we're going to do. Yeah. So. Yeah, what do we end up doing in here? Either way, we're doing something like density estimation, and like it says, a core problem and unsupervised. Like often unsupervised problems, you can formulate in this probabilistic way. And it's a typical framework for thinking about what it is we're trying to do here. So yeah, just like I was saying, explicit density estimation, we actually have a model for P. For implicit density estimation, we actually have a procedure for sampling from it. So producing us arrangements of pixels X that are high probability of being in the actual data set. And again, like, why do this? Well, there's like lots of reasons why. There's a couple of things on here, but really, like, if you can do this, like, it really represents a deep form of learning. You're learning what all the latent factors are that that produce the like in this example we keep going with, the arrangement of pixels that are from this class of like natural scenes, or like in this case bedrooms, or faces of celebrities maybe, or like handbags. There's actually quite a like a zoo of generative models that exist, and we're not going to be going through any of these. There was a nice workshop done, or I guess it was a tutorial done at NIPS a couple of years ago that, or maybe it was just, it wasn't last year, no, this is last year. Oh, that's when the paper was. It was the year before. Where Ian Goodfellow, the original developer of the GANs, did this really nice, like, what is it, like, why generative modeling, and where do the GANs fit in all this? And this taxonomy he produced, it's nice. So, you know, generative models, you might have explicit or implicit densities. If you're doing explicit densities, then you kind of have this family of things. We're going to talk about one of these today. If you're doing approximate densities, then you have a couple different things you could do. These used to be like the models of choice. This is more the model of choice these days, the variational autoencoders. If you're, let's see, if you're doing implicit densities, then you have a couple of options. GANs, which we'll talk about next time, and then there are these Markov chain type models and like various stochastic networks or one of them. But we won't be talking about them because they're a little bit out there. So today we're going to talk about pixel RNN, CNN, and variational autoencoders, which you talked about with Alessandro, and then next time we'll actually talk about it. Okay, questions at this point?
Well, actually, I had a question before, but I don't want to interrupt.
Yeah, go ahead.
The P model X is how do we?
You mean going back a couple slides?
Yeah, how do we actually get that distribution? How do we guess? Like, do we get the parameters from the P data X?
You're just asking, like, how do we even do this thing?
No.
How do we?
We know how to get the distribution of the P data X from the data, right?
Yeah. So we have the distribution. The data is the distribution,
Yes.
or a sample from the actual distribution we care about.
Yeah, and when we do the P model, what exactly do we do?
Yeah. So so what we do is different depending on whether we're doing explicit density estimation. So in explicit density estimation, we're actually learning a function that will, given x, like in this case an arrangement of pixels, that'll give us the actual probability or probability density here, depending on whether we're treating this as continuous or discrete. Like we're actually, like this is going to be a neural network that will take us from the input x to this output, like between 0 and 1, for instance. And in the implicit, that's not what we do. In the implicit, what we typically have is we have some other parameter that is not x. We have some sort of like parameterization of like some latent space that's describing the factors that generate pixels like the class, like our data. And then there's a neural network, but it's going from those parameters that are parameterizing our latent space. It'll produce for us the image like in that part of that space. So it gives us the x. So it'll give us an x. It won't give us the probability. It'll say like, here is something that's likely to be in your data.
Okay.
So we're going to go through this. Like that's the point of these next, like this lecture, and the next one is like the techniques for doing this.
Okay, maybe theoretical. What makes to say as resistance of the density function? Because
say that one more time.
what makes us to ensure that the existence of density function? Here, with both places, we're assuming the density function exists, but usually it doesn't.
Yes, you're just saying like more abstractly, like. Yeah, that's usually an issue not really dealt with the assumption is that there is something that there is a statistical way to describe the relationships. Again, I'll just keep using images. There are statistical correlations between pixel values that need to hold for you to have like an actual image from that you could take with the camera of the natural world, and like if that weren't the case, like I think our human experience would be a lot more discontinuous and like feel like just it would feel a lot. I mean, maybe we wouldn't feel anything because we wouldn't know anything different. So like now it's getting like metaphysical, but like yeah. So like the fact that I could take like the beak or I could take the head off of this bird and like move it down to its feet, like you immediately know that's not right. Right? That's because like there's some relationship between the pixels of its body and the pixels of its head that needs to hold for that to be an actual image, right? Like of something you see in the world. So like those are the kinds of things that we are hoping to learn, that the networks are hoping to learn in either estimating whether this arrangement of pixel values, like estimating the likelihood of it being from the data set, or just being able to generate them from latent factors. And this whole business of like latent factors, I hope to give more meat to. I'm just using it as if like it's something we all have been talking about forever. There's something real there, but we'll get there. Sorry, say that again. Oh, Siamese and triplet numbers. Yeah, we probably will talk some about that next time. So, yeah. Mm-hmm. Do you have a particular interest in those or something? Yeah. Yeah, those are cool. And they're used in a number of cool ways these days, with GANs, for instance, to like estimate when things are on manifolds. I'll just say, I'll launch into one more like really abstract thing, and then we'll move on. So, I've been talking about like this really high-dimensional space. Let's stay with pixels, and that most of the arrangements of these pixels will not correspond to something in the real world, but some will, and you can sort of perturb them. You can perturb the pixel values and still have something that looks like it's in the real world. And that, like the ways you can perturb that, the ways that you can perturb the pixel values are much less, are like the number or like dimension of ways that you can do this is much lower than the number of pixels themselves. And so what you have then is this low-dimensional manifold within your high-dimensional vector space, where the data actually like resides, where the actual natural scenes actually reside. And what we're learning to do here, like in either case, but in particular like the implicit density, is we're learning to like parameterize that low-dimensional manifold with fewer parameters and generate something in the higher dimensional space. And so a lot of what's going on here is like starting from high-dimensional representation of the images, encoding that to the latent space that describes the factors, and then decoding from that back to the image space. So there's this moving between like the actual space, like a local representation of the manifold in this high-dimensional space, but you're using a lower number of parameters to do it, and then back out to the high-dimensional space. And so like things like manifold learning, like they're just like this is just a part of this. Like we are learning to approximate manifolds, or yeah, learning to parameterize manifolds in this high-dimensional space.
So are you talking about data X is from a low-dimensional manifold, or the intermediate representation was from a low?
Well, the Z is the parameterization. What I'm saying is that like the actual X's that like where our probability distribution of SCP would assign high probability, like where it does that is a low-dimensional manifold in this high-dimensional space. So we either just learn how to assign the probabilities in the high-dimensional space, or we learn the latent parameterization of the low-dimensional manifold.
So I agree that's the assumption that allows to work, but so I have a question for a particular case. If you have something, a feature that's discrete, how can you argue it's on a manifold?
If you have a feature that's discrete, so like chemical structures you want to embed in a continuous space. Is that like something like what you're thinking? Yeah. Yeah. So it turns out that in that case, what happens is there's like a many to one mapping. So there's like regions on the manifold that all produce the same high-dimensional high-dimensional representation. So it's not like, it doesn't have this nice like diffeomorphic property that you might hope to have like in some mathematical context, but we also don't care. Like the fact that we can just do it and it seems to work is like enough for some context, but would be like awesome PhD level research for other contexts. Does that make sense? So like something that we do a bunch at Recursion is embedding discrete structures like chemical, like compound structure, molecule, molecular structure into continuous spaces and decode from that. So you have this like in the latent space, there's like an infinite region, well, boundary region, but like an infinite number of parameters that would map to the same molecule. That's okay. Okay. Okay, let's go on to something that's simple, sort of works, but we won't really do anything with it, just other than to mention it. So, okay, so we're talking about explicit density estimation right now. So, one thing you can always do with your data is you can factor it in this way, where so think of our x as like an image, so it's this vector of pixel values, and we can factor that probability distribution in the following way, where the first pixel, so if we put like I equals 0 here, this distribution would be conditioned on nothing. So you would just have like the probability of the prior that this pixel value is just the likelihood of it, and then the likelihood of the first I equals 0 pixel value, you would I guess we started with 1 here, so 1 and 2 would be conditioned on that previous one, and then the third one would be conditioned on the first and second pixel values, and so forth. And this is like a valid, no matter what the distribution is, you always factor it this way. And so this is just something that you can do, like it's just a factor probability, and what we might consider, what we might want to do is learn basically each of these distributions. We might want to learn how to condition our the likelihood of the next pixel on the previous one, and that might allow us to generate data. And so this is something that can be done. So like this type of learning to do this is something that's called a fully visible belief network. So there are like hidden belief networks where you have some latent variables here. You have no latent variables. There's no latent state that's describing that you condition on. Everything here is visible, which is why it's called fully visible, because it's nowhere near this factorization if you have any latent factors. So again, what we can imagine doing is we can learn these distributions via neural networks. To be able to do that, this might seem strange, but it can totally be done. We need to have some sort of ordering on the pixels. Like we need to be able to say like, this is the first one, this is the second one, and then learn the conditioning on that. So here's a way that it's done. Is, you might, let's just think about like a black and white image or something that's where there's only, for each pixel there's only one value there describing like the grayscale or something. So you can think of picking any, you can start with any of these, like it's sort of nice to start with one in the corner. And then you learn this dependency. It's like a sequential dependency, right? You go back to here, this factorization is sequential, right? It's like you take all the previous pixel values and now you predict the next one. And this should feel a lot like a recurrent network, like what we've been talking about, and it is. Or at least this is a way you can imagine modeling this, is that the spatial correlations of pixel values we will actually model in a temporal way. And you can just, so like this is just showing you like how you might think about ordering all these pixels and how you learn to generate this estimation. Excuse me. Okay, so like you can imagine how this would be done. If you've been paying attention, you say like, oh yeah, I can believe that. It turns out like this is probably a really bad idea because there's just so many. There's a couple reasons why this is bad. In fact, let me shout out why you think this might be a bad idea. And these are slow. This is very slow, but there are other reasons why this is probably a bad idea. You're going to use LSTMs or any recurrent neural network to model these spatial dependencies. So what's the problem here? I mean, we spent all this time with convolutional neural networks to learn how to, like, with a small number of parameters, like somehow get the pixel values over here to somehow be correlated with or be influenced by the pixel values, say, way over here, on very long spatial scales relative to the image. Yeah.
Is it because the probability distribution is really like uniform and not very telling? I mean, it just feels to me like what's in the top corner, like on the pixel level, what's in the top corner doesn't really correlate all that much with what's in the bottom right.
Yeah, right. Unless like you have like a tree or something that's like extending from like top to bottom, or like an airplane going from like the bottom corner to the top corner. But yeah, like the issue is kind of the issue is kind of in there, right? So it's like you do like for some of these images, you do need there to be information from here, say where we started, to influence like pixels way over here. And if this is a large image, like your LSTM has to it's like tracking hundreds of like temporal sequential transitions, and that's really, really hard for an LSTM to do. It can do maybe dozens, but it's like hundreds it really can't do well on its own. And there are other architectures that you could use, but just naively using LSTM, this would be like a really bad idea. So you can still imagine doing this, but you can do it instead with a convolutional neural network. So, so here, you basically just use a convolutional neural network like kind of how you'd expect to. Like you want to, like for each of these pixels, you want to predict what should be the next one. You basically want a probability distribution for, like this histogram up here is between 0 to 55. So like you have some value in there for your channel intensity, and you want to be able to predict that. And you want it to depend on like the rest of the image, but you don't want it to depend on anything you haven't seen yet. Because the idea here is you're trying to learn to generate the image, right? So if you learn a convolutional network on the whole image, like we have seen a bunch of times, then you have no way of generating, because it's all generated. Well, there's no generation. There's no like starting from somewhere and doing something. Here, the notion is like we have some prior that we sample from on one pixel, and we start to fill out the rest using this trained network. So it has this kind of strange sequential behavior, or sequential training pattern here, to be able to learn these distributions on the pixel values, and then when you're actually generating, you just sample from this learned distribution there, and then you just move on to the next one. Just like almost in exactly the same way that you would do this for like a language model, where you seed the language model with 1, 2, or just a couple of words, and then it uses this model to say, take that string of words or characters and estimate the next one, and then you shift frames and you move forward and you just keep going. So, I mean, it's sort of strange, but like this is a way of generating an image. And yeah, and the way the training proceeds is just to estimate this likelihood in this way. So each of these distributions that you're learning, like at each of these pixels, it basically depends on the rest of it. And like what's nice about using a convolutional network is you can choose your architecture such that even when you're way over here, you can still have, through like the hierarchy of layers, convolutional layers, you can still have the prediction over here depend on this, because the receptive field of your network at that point would actually include the whole image. Even though this picture shows the receptive field not included a little bit. But that's the idea. So you can learn these like longer longer spatial correlations. Anybody think this seems weird? I think it's weird. But
For the one on the previous page, you say
previous one, you mean like this?
The effect of the lower left, upper left corner pixel is diminishing on the lower right corner pixel. Well, can you think of connecting other pixels and then allowing the probability to propagate on
Like, so in some sense, using, let's see, don't have it on here, but like using a different factorization of your distribution to do those kind of dependencies. Is that what you're suggesting?
Yeah, they were fully connected.
Well, you can't do it fully connected because then you couldn't generate the.
Yeah,
It's like you have there's some notion of sequence here, so you can say like, given everything beforehand, I generate the next pixel. Again, like this is just an approach for doing the explicit density estimation. So like when you're done with this, you actually have a model that is telling you for each of these pixels, given the previous pixel values, like what the distribution, like what is this distribution right here, and therefore the full likelihood. Like you're actually learning to do that. But there's a couple problems with it. The CNN sort of overcome like the slowness and also these longer spatial correlations being learned. It's still pretty slow, and I don't think it's going to come out very well here. But the things it generates it just doesn't look like anything. Like it sort of has some like spatial characteristics of stuff. Remember CFAR 10? Remember like you actually sort of generated some images here, or at least like templates of images. Like yeah, these like if you look at them from afar, it kind of like feels like a natural scene, but when you go close and look at them, you're like, that doesn't look like anything. So it's like close by this manifold of actual natural images, but it's not close enough to be on it where there's like a crisp horse in there or a nice crisp cow or whatever. And then here's 32 by 32 images. So remember, ImageNet actually the images are usually much larger than 32 by 32. But because these models like do struggle with there being accurately learning dependencies between the ends, like the last pixels and the first pixels, this is done on like crops of a much smaller or downsampled versions of it. So again, like if you look at it from afar like you are, you kind of look at it and you're like, oh yeah, that kind of looks like that might be a bird, and you kind of look to it and you're like, that's definitely not a bird. So so it sort of works, but not really. So pros, yeah, you're actually explicitly learning the likelihood, the density P. these are like, yeah, this is true. I didn't actually point this out, but this is an interesting point. So in a lot of what we're going to do next, like especially with the GANs, the way we're going to know that they look good, like we know the way that we know we're doing well is that it's going to look good to you or look good to me. So that's a really bad metric, right? In general, like the eyeball metric does not scale well, and it's hard to quantify. And yet, like we all kind of get it. This says good samples. Like it is way better than say like other things that we've seen so far, but they're really terrible compared to like what we'll be able to do with more sophisticated models. And it is quite slow because of the sequential generation. And there's a lot of like variations on these to like make them better. But let's talk about a technique that's used a ton these days, and it's really a powerful technique. And this is variational autoencoders. So we talked about autoencoders, and we're going to talk a bit more about them now. So okay, so this is what we've been doing. We've been trying to estimate these directly. When we do variational autoencoders, we're not going to have this factorization. We're actually going to think about this as a marginalization. Our likelihood is actually a marginalization of the likelihood with a prior. And this z now, you see the z, and like whenever you're doing machine learning, the z is usually like the variable you go to represent latent factors. Like this is something big. This is something that we don't know, like we don't have direct access to, but we assume that it exists, and it is explanatory for our images. So like something like this is saying the likelihood. So this right here is a prior on our latent variables. This is saying like what are like which latent variables are likely. And then this right here is a likelihood that's saying something like, given this set of latent factors, what's the likelihood that this is the image that's generated from it? And there's like this, like theoretically you can write that down and it feels really great. If you're a mathematician, you're like, finally some math's on the board. But it's a problem. Whoops. There's a slide there. It's a problem because you really can't optimize this directly. And we're going to spend a lot of time right now kind of seeing why. Like one is it's an integral, but you could like imagine approximating the integral in a variety of ways, but there's like really fundamental reasons why this is a very difficult thing to estimate. So let's go through and see this. So let's just start back with autoencoders. So I've talked a bit about this already. So autoencoders, auto is meaning self, so like we're encoding ourselves, right? So we have, there's two pieces to this. There's the encoder that takes us from the input to our latent feature z. We think of it as encoding, like this is extracting the relevant information to describe what's going on in our image. We'll do any data at all, but we'll just continue using images because it's nice and easy. That's what the slides are for. And there's lots of ways you can learn to do this encoding. There's, these ideas have existed actually for quite some time, and these days, like for images, convolutional networks with ReLUs are the typical way of learning these feature sets, these latent feature Z. And like we talked about, like the Z is usually of much smaller dimension, and why do we want to do this? So again, I mean, I've said this a bunch of times, but this is really, really essential. So like, this really high dimensional representation, like this really high dimensional image, there's a lot of pixel values, but like the basics of like what's going on in the image can usually, and this is up for debate from those of you who are thinking a bit abstractly today, but you can usually think of them as being like generated from like a smaller set of things that say like, there's this much of a smile, or like the eyes are this much, think about faces, eyes are this much open, or like the eyebrows are set this much higher than the eyes, and they're spread out, so far, and the ears are set this way. Yes, like each one of those things I described, there's like hundreds of pixels and color values associated with all that, but but in the end, you can sort of just think of those as being like grossly sort of described by that kind of like the thing I just said. And what we hope to do is to be able to, when we look across all of our data, be able to encode that kind of variation into some low-dimensional vector representation. Yes?
Do we tell it then how many dimensions that we want
Yes.
to use it to? It doesn't learn that.
No. Typically what we're doing here is we're saying, like, here's the number of
Slide
dimensions.
vector and
Yeah. Yeah, we'd say like, so maybe these are images that are 256 by 256 by 3. And we might say like, we hope to encode that in 64 dimensions. That might be too low. So maybe we go up to 128 because we always multiply it or divide by 2. And then, like, this is one of those things like just like you would play around with to see a couple different things. You'd want to see like how faithfully you reconstruct your input data. So the decoder, again, these days you learn these decoders with convolutional neural networks, and of course we're like upsampling, right? We're going from these low-dimensional representations back up to this high-dimensional space. So we have to do things like transpose convolution that we learned about weeks ago, maybe months ago, I don't recall. But these are the kinds of things these are the kinds of networks that are used to do that. And then we evaluate like what we're doing by just basically like how close is this reconstructed or predicted image from this. So we encode and we decode. And we literally like it's as simple as this, and it's funny. Like this actually works. This is like a technique that works really, really well, and it's simply supervised by just this reconstruction error. So this L2 loss up there, which is the so you think about, we were representing it this way on the board, but you think about your image as it's a tensor. You can just think about it as like one really long stretched out vector. Same thing for your reconstruction, and you just subtract one from the other, and then look at the magnitude of that, and say like, we want that to be 0. So like this thing would be 0 if and only if they were exactly the same. So that's the loss you're trying to penalize with, and yeah, you can just learn these things, and you can see how it goes. And of course, there are lots of hyperparameter choices to make. Like what exactly is the form of the encoder from here to here? What exactly is the form of the decoder from here to here? What's the size of this, like the number of latent factors? These are all things that have to be played with, but that's okay. After you train, you can imagine throwing away the decoder, but what's also cool about it is now if you take any values, like valid values of z, you can decode that to something. Like the decoder is a function taking you from the latent space back to result 3. So like it can correspond to something. And if you think about it now, like since you can do that, the z now are like some parameterization of this low-dimensional manifold, or just you can think of this as like just each one of these is like an individual factor that's changing what is produced in this image. And we'll see some examples here like how that plays out in some simple data sets. But it's really pretty powerful. Okay, so what's the variational autoencoder on top of that? Well, we so far, like what I've described is simply it's really straightforward. It's really deterministic in the sense of like we're learning a function from the inputs to the latent space back out to reconstructed input. But we might want to think of this more like probabilistically, so that we could think about like one, estimating densities, and two, because like when we sample from this latent space, we might want to see some additional variation. But what the variational autoencoders allow us to do is to take this autoencoding idea and put it into this probabilistic notation or this probabilistic framework. So the way to think about this, So let's think about like the decoding step here. So we have, so the assumption being made here is that all of the training data that we have, it's being generated from some unobserved, some hidden or latent factors Z. And thinking of this probabilistically, there is, we might think of like sampling some value of Z from a prior distribution. So we're kind of in a Bayesian framework here. So we use words like prior and likelihood and things like that. But so prior, meaning like, we're going to interpret it a bit differently, but prior meaning like some prior like knowledge of how we expect these things to go. And then once you have a sample from here, then you want to be able to sample conditioned on those latent factors. You want to sample a likely image or just data, but in this case like an image from those factors. So instead of thinking of it just as like a direct function approximation, you want to think more about this in terms of sampling. Again, the intuition here being X is the image, Z are latent factors that describe it. So these could be like anything that might describe it. Like if we're talking about faces, it could be everything about like color of eyes to orientation of mouth or nose or length of nose. Just any of these things are like things that are valid. And it's funny, I'm falling into this trap too, because just like English makes me fall into this trap. Like what we hope is that these latent factors are actually things that we can describe really easily in English, but they don't have to be, right? They can be combinations of factors that are hard to interpret. And like the smaller the latent space, like the lower number of dimensions for Z, like the more that these factors sort of get compared with each other and are like less interpretable, I guess. But anyways, that's sort of the language we want to think about here. So each one of these things is going to be a network, and our parameters, theta, we are like the goal here is to come up with a good estimate of these parameters that allows us to have a good generative model here. So how do we represent this model? So we have a lot of choices here. Like how we have a choice for like how we're going to represent our prior distribution, how we're going to represent our likelihood. So the way this typically goes is for the prior, you just try to make this as simple as possible. So like typically you just say like, okay, I want to like enforce statistically that like the factors are as like decorrelated with each other as possible. So like a common choice is to choose the prior distribution just to be some like isotropic Gaussian. So or at least like where the covariance is diagonal. It doesn't necessarily have to be isotropic, but at least the covariance is diagonal so that there really is no covariance. You just have so decorrelation between the factors. So you kind of like you try to enforce this on us by choosing here, so that the hope being that when you learn this, whatever factors are here, they are going to be as independent from each other as possible. You can make other choices. Maybe the model is a little bit harder to train, but of course you get a wider variety of like statistical factors. But this is like a typical approach: is to think of the prior as being this very simple Gaussian, and the likelihood here, this prediction of the assigning the likelihood to the pixel, the image pixels given the latent factors. This is what's going to be very complicated and what will be represented by a neural network. And the way we train this model is we train it in very similar to the fully visible belief networks. We are going to maximize our likelihood. Or actually, it's funny to call likelihood. It's actually a little stupid there. But. Okay. So, but this time what we have is we have some latent variables, and like, what do we do about that? So let's go through this. So, okay. So I just want to say this one more time. Like the big difference the big difference from what we were doing before with the pixel, RNN, and CNN is that we actually have a hidden state. We actually have latent factors that we're trying to attribute the variation of the images to. So let's see like what's easy about this and what's hard. So like if we choose this to be a simple Gaussian, we're good. That's like there are closed form integrations you could do, and even if you couldn't, it's easy to sample from because it's just like a very simple parametric model. There's lots of things you could do there. This is a bit more complicated, but at least it'll be a neural network, and at least it'll be something that we can work with and we can sample from or estimate distributions from or whatever. But the real problem is the fact that we're trying to bring these two together and like think about basically like for like to do this integral, we'd have to for each x we have to do this integral over all of the z's. And there are like approximate ways of doing this, but this is like in general this is a pretty intractable thing to do computationally. So related to this, our actual posterior here. So yeah, I guess that's what I'm calling it that way. Anyways, the actual posterior here, which is the likelihood, well, so the probability of the latent factors given the image, which by Bayes' rule looks like that. This also is intractable because you have this addition, you have our, what we call the data likelihood, you have this in the denominator. So you can't just go straight to this either. So like all these things that you might want to like work with these are computationally difficult to work with. So there's going to be some approximations being made, and like here's like the meat of it, the crux of it. So what we're going to do, so in addition, so well we're going to see this in the next slide, but we can think of the network that's estimating P of X given Z. We can think of that as like the decoder network, right? Z is the latent factors, X is the actual image. So we can think of that as decoding, going from Z, the latent factors, and giving us the image. This posterior density, you can think of being as the encoder, going from the image to the latent factor. Like given the image, we can sample from that to get the latent factors. So that's a difficult thing, but we want it. So what we do instead is we actually just assume that there is another network. We're going to call this Q. This is our encoder network that we're going to learn, and we're going to have it approximate this value, or the values here, that density. But it's not going to be exactly that. And that's going to allow us to make some simplifying assumptions here for this that allow us to learn it. And we're going to try to make it as close to that as possible, but it's probably not going to be exact. And as a result, because we're going to make that estimate, we're going to have there's going to create some bounds and errors. But we're usually going to be okay with that because in the end, the results we get are pretty good. So in pictures, what I was just describing is we have this decoder network and this encoder network. And for each one of these, what we're thinking of, what the networks actually do are so in the case of the encoder network, we are going to, from the image, we're going to produce the mean and the covariances of a Gaussian, and we're going to sample from that to get our value Z, so our latent factors. And similarly, once we have our latent factors to decode, we are going to have a network that starts from those latent factors and estimates a mean and a covariance of a Gaussian, and we will then sample from that. And that will give us this mapping to go from input to encoded latent factors back out to input. So we're just going to sample from this. And these have names. I'm going to just go a little bit faster as we need to get through this next slide to have this make sense. Actually, this probably won't make sense at the end. I hope it does, but it will take a little bit of time. So, okay, so what are we going to do now? Well, we need to be able to we need to be able to maximize some probability here. We are going to, and like in most problems, we're going to maximize, say, like the log likelihood. So we want to maximize the log likelihood of our data. Okay, so we know that distribution alone is intractable. So we're going to try to rewrite these things in things that are tractable so that we can do this. So we do this first thing that this is the kind of stuff I mean that's where's that coming from? So whenever there's a mathematical proof like this, it's or equation written down, somebody's done all the hard work of figuring this out, and they put it all back together, and the first line is always what? Why would you do that? But then when you get to the end, it's oh, maybe that does make sense. But maybe at the end it does make sense. So we're going to rewrite this this log likelihood in this way, as the expectation over our encoder network of that log likelihood. And the thing is our log data likelihood does not depend on the latent factors. We've already marginalized them out. So these two are the same, right? This is just, you can factor that in. It's a constant with respect to z, and that expectation is just a 1, and so that's an equality. But doing that allows us to rewrite everything here in some nice ways. Yeah, taking the expectation will come in handy. Okay, so the first thing we do is we rewrite this likelihood following Bayes' rule like we saw in the previous slides. This is just looking like a prior likelihood. And once we do that, we can start to do all these mathematical things that show up in proofs like this, where all of a sudden there's the number 1 showing up as this ratio of this over that. And you're why would I do that? Well, obviously because then you're going to do this. And you're why would I do that? Well, there's all kinds of funny things going on here, I guess. But some of these things are quite nice. So this is something that we're going to be able to estimate right here. We'll talk about it in a second. We'll talk about that in a second. Because we are going to have a network that estimates this distribution. So given the latents, what's the likelihood of the data? But then we have these two terms that just sort of magically appeared from having these expectations and doing Bayes' rule and having this multiplying by 1 thing. Does anybody recognize what these? We've talked about these a bit already. Anybody recognize the form of these things? What? I can't hear you, sorry. Both of these are KL divergences. That's right. So this right here is a KL divergence, and this right here is a KL divergence. It's hard to see this, I guess, in the slides, but this is an expectation over z, and so these two are KL divergences. And what was nice about KL divergences?
It's like a good way to compare to distributions.
It's a good way to compare to distributions. It's not a distance, because this is not symmetric. If I were to swap these, it wouldn't necessarily be the case that the resulting KL divergence would be the same. So it's not a distance metric, but it has some nice properties, like the KL divergence is always non-negative, and it's 0 if and only if the two distributions are the same, or at least almost everywhere. And so what's nice about that is that that allows us to get some notion of where the values kind of reside compared to each other. So so those expectations allowed us to get these nice KL divergence terms. So again, there are ways of comparing the distributions. And here's where it all finally maybe hopefully makes sense of where this is going. So we wanted to be able to estimate that so that we can do stochastic gradient descent. So we want to be able to have that function and take derivatives of it with respect to the weights in the model theta and train it like we like train this network like we train other networks. So what are these different pieces? So this piece right here, this is our decoder network, right? Given the latent variables, like what is the image, what's the likely image associated with it, and we can estimate this. So like there's a model that gives us, so we can estimate this. We can estimate this this expectation because we can basically sample from this. Remember, this gives us the model will give us the mean and covariance for this distribution, and then we can take a sample from it, and then we can keep doing the sampling, and we can get an estimate of the expectation here. So like we can actually do that. And we can actually do that. And then this KL divergence term, this is just between, so like we've chosen this to be a Gaussian, this prior on the latent variables. And we've also chosen the encoder network going from the image to the latent variables. That's also a Gaussian. So this actually has some really nice closed form representation that we can use. So that's great. And then we have this term. And unfortunately, it contains the intractable term, this posterior, given the image, what are the latent variables. So actually, we can't do anything with this term right here. But that's okay, because we know it's going to be non-negative, greater than or equal to 0. So we can say the following. We'll be able to work with this. We'll be able to work with this, and we'll be able just to say that like this is greater than or equal to 0. So we're actually bounded from below by that term on the left. So this is like this represents basically our loss function right here that we're going to optimize, and we're to optimize the log likelihood. And of course, optimizing the log likelihood, we want to maximize that. So this lower bound has a name. It's a variation lower bound. If you've done some like time statistical physics and things like that, you might have run into variational methods. This is a very kind of common theme here. But anyways, this is like called variational lower bound. Sometimes it's called elbow. You might see it called the elbow bound. And basically, we're gonna use this loss function. We're just going to maximize it over the two parameters: the parameters for our encoder and the parameters for our decoder. And like another way, this kind of like all this crazy math way to think about it is this term right here. When we maximize, we're going to be maximizing this expectation. So this is like improving the reconstruction, right? Going from our latent variables to our reconstructed image, the log likelihood of that. So as we maximize that, this is learning a model that allows us to do that better and better and better, the reconstruction part. And then this term, this KL divergence term here, is a divergence between the actual prior that we couldn't estimate like alone. It's our Gaussian that we want it to be, and then we have our this encoder network that we want to have basically be the same distribution with respect to z. So this KL divergence, because it has a negative sign, when we try to maximize that, because KL divergence itself is non-negative, the negative of it is non-positive. So when we try to maximize this is basically trying to make this as small as possible, the KL divergence as small as possible, which means that you're trying to force those two distributions to be as close as possible together. So yeah, so like a lot of weird math, but allows us, so it gives us some lower bound that we can optimize. And you might be saying like, yeah, but like what's happening, like as we change these things, what's happening over here? And the answer is we don't know, but it still seems to work pretty well. Yeah, so that's what we maximize that lower bound. So the way this looks like as we're thinking about training is we have our input data, we generate via our encoder network the means and the covariances for our Gaussian. We are we sample from that to get a Z. Then that, we use our decoder network to give us a mean and a covariance. And then from that, we sample an actual image, and that gives us the other part of this, this estimate. And there's one more thing going on here, which I think also probably, I think seeing his slides, I think you probably spend a little more time in. And you might be wondering about, and that is like this whole notion of sampling. Like, how do you take the gradient through samples? Like, that's kind of like, that doesn't seem like a differentiable thing. And you deal with this with something that's called the reparameterization trick, which allows you to sample from, like for a Gaussian, you can sample from like a standard normal, like zero mean identity covariance. And then by multiplying by the inverse of the covariance matrix, or the inverse of like the square root, I think. I'm kind of forgetting now. I guess it's diagonal is the inverse of it, but by multiplying by that that sample by that and then adding to it your mean, you actually get back a sample from your actual Gaussian that you care about. And so you can actually like factor out the sampling part from your actual parameters mu and sigma, and this is like the thing that makes it all go. And once you have that, voila, you learn this thing simply supervised by the reconstruction error, and now you have a very cool tool. You have, for any latent factor, you can generate samples of images. So like on something very simple like MNIST, here's an example of training on MNIST, a variational autoencoder with just two, with Z just dimension 2, so there's 2 factors of variation. And what's cool about this, what you can see is, like, so think of this like Z1 and think of this as Z2. So like our first factor Z1 and our second factor Z2, or I guess that's the other way here, but as you vary that, you can see you're getting some sort of like the samples that we produce, you get this like smooth variation in various factors, right? So like as you vary Z1, you get a change in the number, right? It's going from basically like down here 1 up through 0. And as you vary this, you also get some change in the numbers, but you also get like some shifting, like some slanting of the numbers. So like what we learned here is we parameterized in just these 2 dimensions, we parameterized some important aspects of the way that the MNIST digits look. And as you pick different values of Z1 and Z2, you generate something like that, having that feature. You can see this also for like more complicated data sets like these face poses where like, as you vary this factor here, the head changes like which direction it's looking, and the degree of the smile in the other direction. And this is actually real. It's like just made up and cherry picked so that you could see like, you go, wow, this actually happens in these models. You can also generate data from this. It looks a lot better. In fact, if you were able to see these, like you would again, like you'd say like, oh, that looks pretty much like what I was expecting, but there are some problems. And this is maybe a little bit more explicit of the problems, is that when you generate these things, you still aren't like crisply on the manifold. You're getting like this fuzziness or this like this blurring, which is a known problem with the variational autoencoders because you basically, because of the approach, like the way that you're learning this here, the maximum likelihood approach. The maximum likelihood approach is computing expectations, and expectations are averages of things. And averages of things tend to blur modes in your data. So if you think about this, like the distribution is like really peaked. It's like if you just kind of imagine yourself being in high-dimensional spaces with your pixels, it's like really peaked around like the very crisp images, I guess. But then like in between those, like it really dips down to not being so real anymore. And what you're seeing here is the effect of that. So like when you sample from this, it's like sampling between a whole bunch of different modes of crisp images, and so you get something that's like the average of them all. And when we go on Thursday, we're going to learn about GANs. GANs, the way that we train GANs is a very different way that tries to prevent this sort of what's known as like well, this kind of mode. It's trying to actually allow you to sample directly from each of these very peaked modes in your distribution. Anyways, this last slide, I know I've got a couple minutes over, I apologize, but lots of pros here. Like one is you can actually do this and you can learn these latent factors, and it's very cool to have latent factors that describe your data. The cons, though, is that like you're only maximizing a lower bounded likelihood, but like here you can explicitly get at that, so like it's maybe worse. And again, like the samples here are blurrier, the quality is lower because maximum likelihood estimation is like inherently an average. And lots of work is being done, research being done, and like lots of big models here. Okay, that's the end of it. And I'm happy to answer any questions or whatever you have. Oh, yeah. Yeah, so probably that like you have your model. So these can be